Hello students, so let's start with chapter 1 of ME515 Finite Element Methods in Engineering. So chapter 1 is just introduction basically, yeah. So we are going to relate with applications, okay. So why do you need that, okay. So basically the need is a lot of need basically if you see the industries like aerospace industry, for example. Yeah, so if you have to analyze the whole aircraft, then it's not possible that actually you find out the exact solution, number one. So you have to have approximate solution. Based on that you do the analysis, and also it is not even if you apply some method, numerical methods, you cannot complete using just paper and pencil or paper and pen. So you have to actually do some kind of finite element formulation to do the structural analysis of a whole aircraft. Yeah. Similarly, in automobile industries, you have uh, some structures here, right? So it also when you ride a car, that means there is some loading, and then it moves. Because of that, there's some dynamic loading is also there. So all if you the forces, and then you have a tire which is in contact with the roads here, there will be a reaction from here. So this is a structural system basically, and has to be analyzed. The stresses, strains have to be within the limits. Yeah, and hence you do the analysis the same way you do with the aircraft. Okay, so here also, yeah, if you start doing just using paper and pencil, you can probably do it, but there may be some accuracy issue. So if you want it to be, your results to be more accurate, then you have to do more detailed analysis. For that you will need a finite element formulation, and you go ahead from there. Okay, so basically right now I'm just in this chapter 1 is one thing is application, also relating it to other courses that you have studied. Yeah. So basically so far, if you look at the other courses like solid mechanics or engineering mechanics, actually this is one step up. Okay, solid mechanics is where you apply loads, you assume a simple beam, so let us say this is a bar. Okay, so let's assume this is a bar. Okay, so the shape, of course this is a 3D, but actually how we study, we assume this to be a bar, meaning that you apply axial loading, and then there will be some displacement is in the axial direction. So for all purposes, basically this is this may be a 3D structure, but actually the behavior is simply like one spring. Yeah, so we can also it looks a 3D, but actually behavior is of a spring only. Yeah, so the spring, you apply a load, yeah, and there is some displacement. This is what the relationship it has, and the relationship between load and displacement is what is known as spring constant. So you say F equal to Kx, where F is the applied load and X is the displacement of one end with respect to the other. Yeah, so this makes a linear system. So a complicated structure, not complicated, but something which looks 3D, and hence you assume that it will be complicated to analyze if you just assume it as a spring, and then it's very easy to analyze. You can do it. So that's why a spring is so much important, so much used in finite element introduction. So we will actually start with chapter 2. We will look at the spring, how any structures can be actually equated as a spring, and accordingly it can be analyzed. Yeah. Okay. Now the structure could be of different shape. Okay, so one example I showed you, which is a circular cross section, which is it has some length, but in this case we are assuming that all the forces are in normal direction. Yeah, so we are not bothered about what is going on in the lateral direction, right? Okay, now let's say this is also one structure. One structure could be something like this, yeah, or you can say some structure is something like this, yeah, or something like this, yeah, and then we are fixing at one end and we are applying a load from here. Then this is a 2D structure now. So now then you have to accordingly, we cannot just equate this as a spring anymore, because if you what is happening is, in this case, if you are fixing here, right, if you are fixing here or you are applying load here, yeah, so then you cannot just have just a spring for that. But if you had fixed here at the bottom or applied load from here, probably we can assume it to be a spring. You can go ahead from there and we can do analysis. We could assume this to be 1D structure, and just equating that to a spring would have been so easy thing to do. It would have analyzed. Okay, so basically, depending on the problem, yeah, so a structure may look 3D or 2D structure. You can assume this is to be 2D structure, but depending on the loading, the problem, if we fix here one end and we apply the force this end, all the forces, stresses, major stresses, means principal stresses, are in this direction only. Then this is a 1D problem. This is a 1D structure. Yeah, so because force is this direction, stresses are in this direction, everything we are interested in this direction only. Vertical direction is insignificant. So hence this is 1D bar problem. Element we can take and we can solve the problem. So right now we are, of course, the element of these things, I will come back to that later. Right now just introduction to the problem, what kind of problems are there, and how do you know what kind of element you have to apply. Okay, now the other example could be that you are fixing from here and you are also applying a load here, right? See here, you are fixing here. So look like this one. Let us say you are fixing here, you are applying load here. Now this becomes a beam, right? This is a beam problem, right? So now see here, we fix here, we pull it like this one. This becomes a bar, 1D bar, or just a spring. Basically, you fixing here, you are pulling it, it is equivalent to a spring. However, if you just do like this, yeah, and you apply load now like this one, yeah, now it becomes a beam. Beam is again, this can be analyzed like a beam, and beam has its own way, right? So in beam, all of the loads are perpendicular to the axis, and this bends because of that. Yeah, so you can apply. Then you will take a beam element to solve this one, right? If you had fixed head like this one, and you had force applied like in the axial direction, you will take a spring or bar element to solve the problem. If you have a problem like this one, you fix it like this one, and you have applied a force like this, like here. Now, if it is like this one, it will bend like this one, it is a beam problem. But if you have a plane now, right? So this is 2D structure now, yeah? And you apply load here. Still you can use it as a beam problem, or you can also use it as a plate. It is the plate now. You fix at one end, you apply your load here, and then it will be a, let us say, plane stress problem you can assume and you can solve it. So all those things we will look at that. So the force, basically the boundary condition, all those things also decide what kind of problem it is. Okay. Now, instead of fixing one end, applying the force other end, remember this is also material. It's possible that we are hitting one side and we want to find out, right, what is temperature here. Yeah, so let us say temperature here is 100 degrees Celsius, here it is 0 degrees Celsius and a steady state, and we want to find out what is the temperature here. Again, heat conduction problem, we are going to solve the steady state problem only. In this course, we are going to solve a steady state problem only, or a static problems for elasticity problems, okay? Or for heat conduction problem or diffusion problem, we are assuming a steady state and we are solving it. So let's say there is a steady state and the temperature is given here and temperature is given here, and we want to find out what is the temperature here, or could be many other things that we will look at there. Maybe here the flux is defined, here temperature is given, and we want to find out what is the temperature at some place. Again, depending on what the problem is, problem could be either 1D like this one, you have temperature for the whole section here, temperature for the whole section here, or flux for the whole section here, and then you are going to find out. You are treating whole section as one point basically. You are assuming everything is same as that section, and you assume this is a 1D problem, you go ahead from that. Or what you do? Or you solve as a 2D problem. And in that case, what happens? This is everything what you see in this 2D structure now. Then you have to define everything. You have to define like here you have to know here what is the temperature, here what is the temperature, here what is the temperature. These are all boundary conditions. Earlier in 2D, boundary condition was here and here only. Now if you assume 2D, this also becomes a boundary now. So you have to know the boundary condition here and here also, and equation will change. The first case, it will be linear, so it will only the variable is the, so that will be just x, right? So independent variable will just x. But as soon as you assume 2D problem, there will be a second variable, y variable, right? The independent variable, and hence the differential equation will be different. Similar, but there will be one more term for y, right? So all those things, variation is possible. Similarly, if you go for something 3D, let us say you have to analyze this. So now this is 3D, yeah. So let's say you have to do the heat conduction analysis. You are loading this, let us say this side. You are hitting it here. It is exposed to like ambient condition. Here there may be some other convective heat transfer is going on. All kind of things can possible on all phases, right? All boundaries. And then in that case, if that is a thing, it's no more 1D or 2D, it becomes a 3D because it has 6 phases. Okay, it could be more than 6 also because of many complications, the complicated surfaces are also there. And then you have to analyze it. Yeah, so then you have to go for 3D. Yeah, and accordingly your equation has to be also be 3D. Okay, so basically what we discussed is the one thing is the structure, how it looks like. A structure could be look like something like this, yeah, which has like circular cross section. This is 3D. Actually, in real life, everything 3D only, but we simplify it. For example, here, either you can solve it as a 1D problem. So, provided the forces are also in the one direction only. If forces are in two direction, then accordingly you have to change. So this, if all the forces are in axial direction, you assume this as a spring and go ahead from there. If you fix it here, you apply a load here, this becomes a beam now. Yeah, and if you have a there could be combination of that, right? You can also have a torque. In that case, you have to formulate differently. You can have an axial load plus beam as well. So you have to treat it like a frame. Basically, frame is something like a beam only, plus it can also have a axial stresses or load. Yeah. So depending on the problem, you have to formulate. Yeah, of course, you can combine together. So meaning that if you study just for axial loading, how it behaves, just like a spring, and then if you develop finite element formulation for bending, if you have that, and for torque you combine them together, and what you will have is, regardless of what kind of force you have, whether it's torque or bending or axial loading, all kind of forces can be applied, we can analyze it. Yeah, so that's what it is. So, so far we have seen that a complicated structure is being replaced by a simple model. Yeah. Okay. Now next thing is if we have a complicated structure. Yeah. So 2D structure only, but let us say we are now making a truss. Yeah. So it could be something like a structure, something like this one, which is fixed here, like this one. Yeah, and there may be a load here. Yeah, okay. If that is the case, then we have here two springs. One spring is here, one spring is there. Right? There were system of two springs, and then they can be combined. They can be analyzed like that. Also, you can assume the whole thing as not only one spring, but multiple of a spring, right? Multiple of a spring. And the idea is, if we know the property of one spring, which is a component of multiple spring that this object is being represented by, then we can solve the whole problem. Okay, meaning that, let us say if there is a plate like this one and we are going to fix it from, or let us say we are going to heat here, okay, and here we apply some kind of flux, yeah, and then we want to analyze what is the temperature. Anywhere if you want how to calculate that, okay. Then what we have to do is the domain of that divided into multiple, what we call it, elements. Yeah. So now the whole thing, let us say this is being represented as a combination of 8 square element. What you see is one element looks like this one, and now the whole structure is made of 8 such squares. Yeah. Now the idea is to know the property of just one of them, and then after that I have to just repeat it. Yeah. Okay. Now we are talking about the temperature now. Yes, temperature is the one which is a variable here. Now how we will formulate this one? Just like here, if we had like let us say we have to analyze this one, and we can divide that into two springs. So one spring here, the other spring here. And for this, we know that if there is a difference in displacement, there will be a difference in that displacement multiplied by k is the force passing through it. That we know. Yeah, so we know x1 minus x2 multiplied by k is equal to f. We know that, right? So we know the property of 1. And that really means for both of them you can write an equation which if let us say x1 here, x2 here, x3 here, I will come back to all those things. Right now I'm just relating with objects only, but I will finally do all those things on the board. So this is just to introduce you to finite elements. It is not chapter 2, chapter 1, just introduction basically, just what it is, what the course is. So x1 here, x2 here, x3 here, and x2 minus x1 multiplied by whatever the force constant of this multiplied by that is because we have force. And similarly here x3 minus x2 multiplied by k, this will have k2 basically, different stiffness matrix stiffness it will have, okay, will be equal to a different force, yeah, depending on that. But what is the condition? Condition is the force will be the same. Once you have here, if you apply the force, there should be same force so that it will be in equilibrium, right? If you look at one of here, so ultimately the whatever force here should be force here, should be the force here. Okay, so if you are not applying any force here, only force you are applying here, so regardless of which section you take, it should be the same force. So automatically F1 becomes equal to F2, and you solve and you will get x1, x2, x3. x1, since you are fixing x1, you begin with x1 you are assuming to be 0, and hence you will get the other things, right? So this is the concept, right? So you did not get displacement everywhere, but what you got? You got displacement here only or here only, right? Here you are giving, here x1 you are prescribing, x1 equal to 0, x2 you are getting, x3 you are getting because of the force, but you don't know what is the displacement at other points. In order to know the displacement at other points, you will have to extrapolate from here or interpolate from here. If you know that for displacement here and displacement here, you can interpolate between that. And similarly here this is what the finite element does. Okay, so it will be more clear as you go. Right now just introduction, just it is just we are making some background so that we go there, so then we don't wonder what we are doing there. Similarly in 2D problem, right? It's 2D problem, could be any kind of elasticity problem. Here also what we are doing, we are studying just one, so one element. So this is known as, this corner known as node. Okay, here also where the two elements, one square here is element 1, 2, 3, 4, 5, 6, 7, 8, and where they meet, the corners are known as nodes. Yeah, so these are elements, 8 elements, and node 1, 2, 3, 4, 5, and similarly here 5 here and 5 here, total 15 nodes and 8 elements. So node is the connection between two elements. Yeah, so what we get is one element you get here, right? So here you go. So this is one element, yeah, and what you have to do is now for one element we can find out relationship between what, like in a structure, in a spring we have relationship between force and displacement, or can have the relationship between the stress and displacement, yeah, or force and displacement. And similarly here for heat transfer problem, we have to find out relationship between temperature. Yeah, so we will have temperature and then we will have flux. So force and displacement, flux is kind of a force here, and temperature like a displacement. So what is the relationship between them? Meaning that, as you know that, now when you combine it to the rest of them, you don't consider that they are connected at any other place than the nodes. They are connected only at nodes only. So whatever is going on through the node only. Okay, so node is the connection there. All other places, they are not connected. Meaning that the problem now, what happens is you are establishing the relationship between the temperature here, 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 4 temperatures, with the also the flux at these all 4 nodes. Meaning that how many variables you have? You have 1, 2, 3, 4. There are 4 temperatures. And there is a relationship between these 4 temperature and the heat flux. Okay, so heat flux bill, the bill depend on this temperature only, and some constants, some other constants will be there, conductivity and all those things will be there. So basically that relationship we have the Q, X, Q, Y, there will be 2 of them in flux in X direction, flux in Y direction. Both of them will be depending on temperature here, here. Meaning that we have a model where the dependent variable temperature are the one to be found out given some kind of some temperature may be known, or at some surface there may be some flux. Yeah, even if at some surface there is a flux, has to be finally we have to bring those flux to these points only, because we know that in finite element everything is through the nodes only. So all the flux has to be known as the node only, but not the any other place. So even if it is a given, we have to divide some to one node, some to other node, and so on. That's what we do. So basically what happens is a continuous system becomes a discrete system. Okay, a continuous system where temperature is defined at everywhere, we are now reducing that to only 4 points in this example. And the idea is to find out these temperatures at these points only, because we have the equation now which relates the heat flux to these temperatures at this point. And similarly, if all of them are similar, exactly the same element, same shape, so we just have to repeat it. What you have to do is, this is local. You can say node number 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, so some local numbering. But what you have to do, they have to assemble them together. Meaning that equation due to this one, you know, similarly equation for this you know, equation for this you know, always similar. However, now you have to also see the global numbering as well, because together you have to solve. So you have to see here 1, node 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Here you have equation with the local numbering, and you replace that local quantity into global quantity, meaning that node 1, let's say you call it T1, you call it T2, T3, T4 for temperature. Now in global it becomes T1, T2, and this becomes T6, T7. Yeah, and then you find that you write the relationship new in the new numbering system, global system. You write the equation. Hence, you will have how many equations? You will have 8 equations, right? All those 8 equations, and then you are going to to basically solve them. Okay? Solve them with some conditions. And what is the conditions? Condition is, let us say, at this point, what happens? Total heat has to be conserved, right? Same as in this case, at let us say there is no force applied in between here, you are fixing here and you are applying load here, then at that a common void, total force has to be 0 because there is no external force, right? Total force applied has to be equal to 0. Same condition here will be total flux at this point here, or heat loss or heat gain at this point has to be equal to 0. Meaning that whatever heat is going out of this surface will be the heat coming to this surface, hence the net flux will be 0. Because if for this, let us say, if this is a negative because it's losing it, this will be positive because it is gaining it. Hence you add them together will be 0. So that condition if you put, okay, that condition has to be put, and automatically it will solve all the problem. Automatically it will tell you what is T1, T2, T3 after you have so many equations now and you have this condition, and after that it will be a matrix basically because a lot of linear equations are there. You have to solve using matrix system only, and then you solve it. Yeah, and that's why that is the beauty of this finite element analysis, that any big structure can be solved like that. The same principle. What you have to do? Find out one element. Okay, so take out one element from here. Okay, do analysis of that. Analysis means either you can do analytical formulation, or you can go to the lab also, you can do it. And how, I will tell you in chapter 1. So basically, it's possible that you can evaluate, instead of doing numerical analysis, writing equation, finding out what will the stiffness matrix and other matrices, you can basically, you can have one structure like this one, you take out one of it and take it to the lab and you do some analysis. And then you just write it down some matrix, and based on that you can analyze the whole thing. It's possible. Okay, so because this is not abstract, this is some what we are looking for, just how the force and displacement related, or how the temperature and flux related, or how the current and voltage, potential difference or voltage related, or how the pressure and fluid velocity related. So all kind of things, right? So all have same principle. All have same principle, meaning that if even if you take a conductor, right? So let us say you have a conductor like something like this one, yeah? And you assume that there is only one conductor here. Okay, so it may have some resistance. Let us say it has resistance. So the current what is flows through that is proportional to the difference in the potential. Same as the force is proportional to difference in the displacement. Same as the flux is proportional to difference in the temperature. Same as the velocity is proportional to difference in the pressure inside a pipe. So all looks the same basically. If you see all system, all those things are actually the same basically. What is the difference? Always there is something at these two ends. You have to take the difference, and there will be something passing through it which will depend on that difference. Yeah, so all of them have similar kind of setup. Yeah, and hence it's possible, if you know to solve for one thing, you should be able to apply the same thing to other kind of system. So this is just for introduction, so more when we actually do chapter 2, we are going to now write equations and go from there. So this is, here there was no need to write equation, all those things, because chapter 1 I'm not going to test and anything. This is just to relate basically what we are going to do, and so that you set up your mind accordingly, and accordingly we apply there. So you wanted to see the big picture, why we do and how we do, what is the philosophy, and when as we go progress in this course, we will see more and more, and I will try to take different kind of examples as well, and let us see how it goes. Your feedback is welcome, how you like this. I may try different kind of things, okay, so depending on your feedback, I'm going to settle on something, but first few lectures may be some experimental thing, basically just experimental thing does not mean that I will go to the lab, and not like that. What I mean is, first I will try whiteboard, try something like this one, or on iPad screen I record, all kind of things I will try, just to help basically whatever the best that I can do for recording. Yeah, so that is all for today. So this is chapter 1. I consider it to be finished. It was just introduction. Question will not be asked from this chapter. We will start chapter 2, okay, next time, and I will post that. I will let you know when. Okay, that is all for now.